Hello, Flat Earth researchers, debaters and debunkers. Most of us grew up believing that we live on a globe Earth because the heliocentric religion used scientism to make a pseudo-connection between geometry and our subjective view of the Earth perspective. So really, there is no relationship. They are distinctly different. When you look at reality and you look at how our eyes work, you realize a few things. Firstly, that the horizon is your eye level. The horizon is this apparent convergence, and it really just shows you where you are, your height in relationship to everything else around you. That's what it does. It doesn't actually matter what shape the Earth is. It could be concave, convex. The horizon is your subjective eye level. And so it appears where you are in relationship to everything in the foreground and the background. And so we can talk about the eye level as the height of the observer's eyes. You can talk about this in terms of physical height, but also we all know when you look at it that the horizon is at your eye level. It's going to be different for every individual. Okay, so it just tells you where you are in relationship to everything else around you, regardless of the shape of the Earth beneath your feet. In fact, even if you didn't have an Earth beneath you, you would still see this apparent convergence. So here we can see that you've got two people. One standing up has a higher line of sight than the person sitting down, or a higher eye level than the person sitting down. And so they each have their own individual horizon in line with their line of sight. Now, if you take a camera, for example, and you set it up to be horizontal, then you will see this convergence, the horizon, at the center of the field of view, no matter how high above the Earth you go. Even if you go to something like 40 or 50,000 feet, you might not be able to see the actual Earth anymore, but you will see the clouds that are beneath you appear to converge with the clouds that are above you, or whatever is above you at that height. So it doesn't matter how high you are, and it doesn't matter what shape the Earth actually is, you will always see this apparent convergence to tell you instinctively where you are in relationship to everything else around you. That's simply how our eyes work. So another important thing to understand here is that this is a side-on view, right? It's not the actual view that you have through your eyes. We are just illustrating how a person's line of sight is their horizon at that particular person's eye level. And again, here what we have in number 2 is a geometric illustration in which it's also a side-on view. So this is part of the bamboozle. This is where the confusion occurs, because what we're doing here is looking at these side-on views and then in our minds interpreting it into how we see horizons in front of us, and we're imagining that they are curvature. But in reality, in fact, no one has ever been able to measure any curvature. You can't actually start seeing any curvature where someone would see a horizon, because this connection simply isn't true. It doesn't exist. There is no curvature to be measured or seen anywhere on the Earth. It only exists in our minds because it's been put there by mathematical abstract concepts. All right? So, in the mathematical sense, of course, what we have is a circle here. We've got the center of the circle, we've got a radius, and then we've got the height of the observer, and then you would have a tangent line going from that observer to a point across the surface of the Earth at a certain distance, at which we can say that is where that person will see their horizon. Again, this doesn't actually fit with reality. We can see further than the horizon is supposed to appear, and there is a change in what we see, but the horizon always is your eye level. So in this sense, of course, it does become quite predictable, because once you have the height of the observer measured or assumed in an illustration or a model like this, and you have an assumed radius, for the Earth it's 3,959 miles radius, and then you have this length of the tangent line this line here going from the height of the observer and going across this arc length here, this part of the circle that is between the observer and the point in the distance, and then we have this angle created here for that. And so again, you can get very accurate results by using this kind of model, and so it would all appear to work, but it doesn't fit with reality. The horizon you see in your eyes has nothing to do with the tangent lines in geometry. We do not look down, there is no horizon dip to talk of. All of that is just excuses and obfuscation to ignore the reality of the way we see the world, and that horizons are your eye level. So it doesn't matter if you're in an aircraft flying at 45,000 feet, your horizon will always be at your eye level. If you're using a camera and you tilt that camera, then the horizon in your field of view will either rise or fall to the top or the bottom of your field of view because you've tilted it, but the horizon still indicates your eye level, your height compared to everything else around you. And so let's have a look at how we actually see horizons. I've just kind of done some colors here to show what we are seeing. So this, of course, is the kind of view you would have from your eyes looking forwards. It's not a side-on view anymore, so ignore these side-on views for now. But apart from the fact that what we are looking at here is now how one of these people will see the horizon in front of their eyes. So we've switched, and that's part of the bamboozle. It's just this switching of the orthographic views that we are given into this assumption of what we are seeing in front of us. So you can see from this we've got clouds up here, and you would know that the larger clouds that are appearing higher up in the field of view are actually closer to us. So you can see that as those clouds get further away, they would appear to get smaller and smaller and closer to the horizon, which is basically this band of convergence between the sky and the water in this case that we can see in front of us. So what I've done here is you can see that obviously the water in front of us would appear quite spaced out, the waves, but as you look further into the distance, then everything appears to get more, oops, and just get into the camera, more and more condensed in the distance, yeah, you see, and this does change with our height. The higher up you go above the surface, the further you will see more detail across the surface. But so you get this compression. So let's just assume we're just standing on the shore here and we're looking across this water. And then what you have here is, what I've done in purple here is you get mirroring. We are not quite at the center of the field of view yet. This is mirroring that appears on the surface. So what you end up with, I'm just going to choose a color that's suitable, is basically this here, where this mirroring begins, is where when you're close to the surface you see this horizon on the surface, okay, and beyond that you get mirroring. So what's actually happening is you can still see the surface, but you can't see any detail on the surface. What you end up seeing is a reflection of what's going on in the sky above the surface at that particular distance, okay? So this is often passed off as a horizon dip because there is this apparent horizon that appears slightly below eye level. But really what that is just the limit of the distance we can see across the surface, and then we get mirroring that occurs beyond that point and up to this point of convergence, which I've illustrated in red here. So this purple down here is still the surface. It's just that we can't make out any detail, and it's mirroring what's above it. And then we get to this band of convergence. That is the horizon. That's where the surface and the sky appear to converge in our field of view. So what you'll always see and can measure optically when you look is that this band of convergence, or apparent convergence, it's not really happening, is always going to be at the observer's eye level. Regardless of how high they are above the Earth, you will always see this band of convergence in the center of your field of view. Of course, as things get closer to this band of convergence, then they become blurry and distorted. So this is why you would have, if you had a ship that was going off into the distance, it will become very distorted. And of course, the height of the waves will also make a difference as to how much of the bottom of a ship you could see. Even though the waves might appear to get smaller, they could in fact be larger as you get further out to sea from the shore, but we wouldn't necessarily see that, but they would end up blocking off the bottom, or even an entire ship if it was far enough away and smaller in its angular size than the waves that are in the foreground for our subjective view. So do not let anyone tell you that there's a horizon dip. There isn't. What you can see is this line on the surface that appears to be the horizon, but you'll always see mirroring beyond that before you reach this band of convergence. Okay? The horizon, where everything appears to converge, is your subjective eye level. Has nothing to do with the tangent lines that are illustrated in geometry. Even though it's very accurate and predictable, it doesn't actually fit with reality and the way we see the real world. Hopefully that's helped distinguish between the two. Thank you very much.